So the section 6.2 talks about transformations. And I skipped every other transformation that we have talked about. Every other transformation section in the textbook we have skipped so far. I am not skipping this one. What I'm going to do now is I'm going to talk about all of the transformation sections that we have skipped. Can anybody remind me of the transformations you learned for geometry in middle school? What's one of them, Harry? So reflection. Dilation. Rotation. Hunter, did you have another one, or was rotation one of yours? Kind of like. So we don't use middle school slang terms anymore. So your middle school terms are in blue. Flip, spin, and slide. High school terms are in black. If I ask you to describe a transformation from now on, please do not use one of the blue words.
What's
Dilation.
No, like I mean.
Spin, flip, side. No. You got flip, spin, slide, straight, or dodge. Good.
Or stretch. So dilation covers both shrinking and stretching. Okay. There is a special property for these three. These three translations are called isometries. These three transformations are called isometries. And an isometry preserves angle and segment congruence. So if you're using one of those three transformations that are on the left-hand side, the new figure you get is going to be congruent to your original figure. So the reason why I skipped the section on reflections, the section on rotations, and the section on translations is because it used an entire section to say the exact same thing for those three things, which are those three things maintain congruence. A dilation preserves angle congruence, but not segment congruence. In a dilation, segments are proportional to the scale factor. So if I have a scale factor of 2, that's a dilation. That's going to make the thing bigger. If I have a scale factor of 1/2, it's going to make it smaller. And if something preserves angle congruence and the side lengths are proportional, that means those two figures are similar.
That's correct.
So those three dots that are in a triangle is the word therefore in math. So therefore, those figures that you get from a dilation are going to be similar figures. When we did our constructions, you figured out how to do a rotation and a reflection. Today I'm going to show you how to do a dilation using a construction. And to me, a dilation is the one that is most intuitive between the rotation, reflection, and dilation. So it's actually really intuitive. Once you see it once, it's really kind of straightforward how to do it. Any questions on what I have on the board right now?
Hold on.
Do you have this side, Sean?
Yeah. You could resolve it now.
Okay, first thing I want to talk about is notation. We are now going to, instead of using different letters for the two figures that we get, we are going to use the same letters but with some notation to them. So the two terms I want to talk about are the pre-image and the image. The pre-image is where you start. So these are my starting points. The image would be my endpoints or ending points. If I had this triangle that has this as its pre-image, its image, I'm going to make it smaller, would have little prime symbols next to it. So that way you use the same letters over and over again. You don't have to come up with different letters. The A is going to match with the A, the B is going to match with the B, the C is going to match with the C. The way you calculate your scale factor is you are going to take a length of the image, so the length of one of the segments of the image, dividing by the length of one of the segments in the pre-image. So if the image is bigger than the pre-image, you're going to get a number bigger than 1. If the image is smaller than the pre-image, you're going to get a number between 0 and 1.
Yeah.
Any questions on our defining stuff right now?
No, sir.
So construction. Hunter, name me a type of polygon between 3 sides and 5 sides.
Oh, what? Hexagon.
Okay, that has 6 sides, so that's not between 3 and 5. How
Pentagon.
about you? So a 5-sided figure. So what I'm going to do is I'm going to have a 5-sided figure. I just arbitrarily drew these 5 points.
It's okay.
Because that's a pentagon, correct?
Mm-hmm.
Oh.
Harry, give me an integer between 2 and 5 inclusive. 4.
Correct.
Nikki, inside or outside? Okay.
I'm going.
This point that I just drew is the center of dilation. That center of dilation can be inside your figure, it can be one of the points on your figure, or it can be outside of your figure. But the steps to draw a dilation are all going to be identical. First thing that you're going to do is you're going to take a straight edge and you're going to connect your center of dilation to run through every one of your points that are on your polygon and go through and beyond them. Because any dilation that I have you construct is going to have a scale factor that's more than 1. So you're going to actually expand your figure. So I'm going to draw all of these wonderful segments.
That looks so beautiful.
I am not using a ruler. I'm using a straight edge right now. The next thing I'm going to do is I'm going to use that wonderful scale factor that Harry gave us. I'm going to use that wonderful scale factor that Harry gave us to come up with my new points of my polygon. So Harry said 4, right?
Yeah.
So you're going to use the compass and you're going to measure this distance. Okay, that's 1. Then you take that same distance and you go here to here. And that would become
2.
And then you do this.
3.
Then you do this.
4.
And there's your point.
Ooh. No way.
Yep. Then you're going to go here, and that's 1. So that distance to that distance is
2.
to that distance
3.
to that distance.
4.
That's my point.
That looks.
See how you've got to draw the lines long? Okay?
Oh, why does that look so much longer?
Because look at the distance here. Isn't this a lot longer than this distance?
Oh, snap.
Yes. And each line is going to end up 4 times as long as their originals.
Oh, man.
So if that's 1, so right now, cool for it. This one is right here. That's 1, 2, 3, 4. Maybe not off the board there. Except that point is the back end of the polygon. This one would end up off the board down here. It would end up down here on the floor. And I would end up connecting them. And each one of these segments is 4 times as long as each one of these segments that are in that one. So I will tell you on a test, the most you're going to do is 2 or 3. I'm going to give you integers. I could even give you halves because you know how to find half the length of a segment. How do you find half the length of a segment? You find its bisector.
Yeah.
Now, here's where a lot of the similar figures are going to come from today's work, is they actually make one of the points of your polygon the center of dilation. I am going to say that this point right here is my center of my dilation, and I want it to be 3 times as long. So again, you do the steps the exact same way, and you connect your point through the other points. You connect your center through the other points, and then you take your compass. That's 1. That's 2. 3 would be here. 1, 2, 3 would be here. And then notice here, this triangle here and the big triangle are similar to each other.
It's just bigger.
This triangle is 3 times as big as the little triangle.
Oh, now I understand.
What? But this one is actually 1/3 of the distance. So it's not a bisector, it's a third sector. But again, this line is going to be parallel to this one. Okay? Same reason why my bisector lines were. So using this fact of how most of your things are constructed, what I'm going to do is, let's say that this is 3 and this is 4. If this total distance is, I'm just going to call this total distance 10, I want to know what this distance between here and here is. We are going to use the exact same facts that we used for similar polygons yesterday, and we know that its corresponding sides are the P word, proportional. So I know I know this big segment over this big segment is equal to the total segment over the total segment. Okay, something to be careful of. You can't do this over this equals this over this, because they're not both triangles. Notice I have a big triangle and I have a smaller triangle. This smaller triangle has a side of 3 and 4. This bigger triangle has a side of 10. And what's this total side length? 4 plus what? 4 plus x. So I need to do this over this equals this over this. Okay? Some students think, hey, if this is 10, that's 7 and that's 3. And they try to set up the relationship that x over 7 equals 4 over 3. We're going to do that, and we're going to see if that's actually correct after we do it the right way. So I'm going to do right over right equals left over left. 4 plus x over 4 is equal to 10 over 3. First step is to multiply both sides by 4. Next step is to subtract 4 from both sides. (40 minus 12 because that's 4, is 28 which is 9 1/3 for those of you that don't do fractions. So that's how big x is. Now let's see if we set it up the way that some students think. Let's do this big segment over this one equals this big segment over this one. What's my one step to solve that equation? And what do you get? Okay. I can do that, but you don't have a theorem right now that tells you that you can do that. Okay? Your theorem is only between similar figures. What I'm going to do now is I'm going to draw these two figures where one of them looks like this, where you had a side of 7 and x. The other one looks like this, which is a 4 and a 3. Are those two similar figures? Do we have a theorem that says I have two figures that don't look anything alike that are pieces are proportional? No. This only works if the piece that's cutting the two figures apart to make that single figure is actually parallel. If this piece is parallel to this one, then that will work. Okay? Your book never covers this part. This is a shortcut. Okay? Theoretically, I would have to write a proof for that, but we're not going to use a proof for that. If you have two pieces that are coming out of the same figure, just make sure you set up your relationships properly. Okay? And again, I said this whole distance is 10. Don't do x over 10 equals 4 over 3. You actually need to do x over this distance, which is 7. Okay? So make sure you set up those things properly. One other thing I want to talk about, those first three transformations, our rotation, our reflection, and our translation. Besides calling them isometries, they're called rigid transformations, which means that nothing moves. Well, they slide around like this, but none of the pieces move with relationship to each other. They're all locked into place, no matter where you take that figure and move it around. So another name is rigid for those. Dilations can make things bigger, and they can make things smaller. Okay? We saw this dilation where the figures have nothing in common. We saw this dilation where they have a point in common. You can also have a dilation where the center of dilation is in the middle. So if I extend my lines through all of those points, and then I, let's say, just double this distance, and then draw my new triangle, notice that these two triangles, one's going to be inside the other. So those are the three possibilities for centers of dilation. Yes?
Is there like a construction for making it smaller?
Yes, but you would have to be able to, the only constructions I would have you to make things smaller are to actually, you'd figure out what this distance was, and you'd have to do powers of halves. So I can have you make it half as big, I can make a quarter as big, an eighth as big. I can have you make it 1.5 as long because you can take one of the distances plus the bisector for another half, but I'm not going to make you do that extra work on a construction. But yes, you can do that. Not as a construction. If I were going to have you make something half as big, I would actually let you use a ruler to measure the distance. Let's say this was my original figure. I would let you use a ruler to measure the distance between there, and then take half of it to get this. But on making things bigger, I'm not going to let you use a ruler. I'm going to have you use the compass to lay off the measurements. Okay, for construction purposes. Are there any questions on dilations? We're done.